So he says he's running 7 minutes behind, so just conservatively, let's plan to start at 6:40, just FYI. Sorry.
There's some leftover O'Reilly swag that I keep trying to get rid of. So if anybody wants any of that, if anybody uses H2O, there's a learning guide and some notebooks.
it's underneath me. It says I'm connected to the USF guest network, but I can't SSH over it or use Ajax type stuff. And these guys, right?
Are you going to try to abstract it up few levels, patterns of interest?
No, I don't have anything trained to do that. It's just me. So these, it's just a statistical. You might say a statistical correlation, and then if I have a push to pull up group pairs, but on the duration space, but.
See what you're
So I might do something like that and then improve on the previous one. Let's see what I have to like. This square has grayscale. So I can get a few grayscale matches to that one. See, textual stuff with grayscale. This corner sort of stochastically varies between hue and saturation 24 by 24 and 48 by 48 for the resolutions. So this next one is going to be 24 and 32.
so magical when I saw it in the abstract.
That's like the code of like the pictures.
So you do exotic
Right, that's right, very basic, so that people use that, you know, the workbench to add like more real intelligence to training something.
Yeah.
Start working rationally, that's just key parts of it. You gotta.
Very curious.
You haven't missed anything.
Yeah. So this was a much smaller. This was a mini summer house. So this was like kind of like Phoenix. They actually done this whole thing. Or we only do it.
Tower of Babel, where the humans wanted to reach happiness, and it does.
Small scale, if you see them, there's something like that in the back.
It wasn't
Proof that you like training. If the training is something.
the difference was that they were so really small, like less than a percentage point better than the most whereas that was decided the end and stuff that so way to go in that order. So you have to be right. We go we have a bit of running that the traction is like it was the users get access to the start and last that's
In a way,
and also was like service so we can find users request to ad hoc so that the local account can say hey this starts with a good term to do this.
at some point,
So
it's
it's
usually possible.
like this chapter.
Hello everybody.
Which one do you want? I thought this one was better.
display point.
Oh, okay.
It's called display point. Cool.
Okay, hold on for just 1 second.
Now the table shows the
All right.
instead. Forget this. The chairs were put on. Take your chances on this one. How far up, how far.
Oops. Do you want a microphone? Yeah, a little bit louder.
Testing, 1, 2, 3.
Yeah, we definitely hear you. All right,
Okay.
guys. Oh, before we begin, I just wanted to let you guys know that next week we're going to be meeting on Tuesday. I know it's a little unusual, but because of the Labor Day, the building is going to be closed. So same time, same room, but on Tuesday. And we're doing this backwards thing where we're doing chapter 14 now, and then we'll do chapter 13. But then we'll start the normal way, 15, and so on and so forth.
Oh, and if somebody wants to go over chapter 13, please sign up. I was kind of forced to present.
No, there will be no forcing. I promise. Okay.
Okay, so Autoencoders. So it's kind of a very classical and a simple model that people tend to start with. It has not many practical applications, but it's very simple to implement. And basically, when people start playing with neural networks, they tend to start with autoencoders. And because of that, there's a lot of research around them. They can generate some pretty pictures. So it's good to understand some concepts behind it. So what is an autoencoder? So the idea of autoencoder is that you have some input X. So let's say your neural network with 2 layers is written like this, G of F of X. So maybe G and F have some parameters, and in traditional supervised learning, you adjust parameters to try to fit your Y. Autoencoder replaces your Y with X. So essentially, you're trying to, when you minimize your theta, the minimization problem you're solving is G of F of X, Y, minus X of I. So let's use square plus. So here's a simple example. So in traditional supervised learning, for instance, you're trying to fit some points with a curve. You're trying to fit your y's and x's are separate, and with autoencoder, you're basically trying to fit, produce the input. You're using input as the labels. So as a simple example, what can this function g and f look like? So simplest example is a linear autoencoder, where you simply use a linear transformation of the input. So you're saying, let's say, the middle layer, some pictures. So this is x,
then you have some h, and then this is y, and in the case of autoencoder, it's the same as x. So simple linear autoencoder, you're saying h is equal to w times x. So essentially, your x is a vector, and then you're multiplying it by a matrix, and you get some vector h. And then this is this, and then w1. And so this part is called the encoder. So you multiply by a matrix, you get some number. That's your hidden layer. Hidden layer. And this direction is called encoder. And now h of some value. It's h, let's see, is equal to w2 times z. And this part is called the decoder. So it's called the decoder because when your autoencoder fits the data, when you put Z in there, you will get your original X. So suppose you're using linear autoencoder on this kind of neural network. So you have 2 dimensions here. Here you have 2, and then 2 and 2. So your W1 is essentially it's like 2 by 2 matrix. 2 by 2, and same with W2. So can somebody guess what would happen if I had this kind of architecture and I had some data, for instance, random data, and I was trying to minimize this loss?
Come out as an identity matrix.
Right. So what would happen is that you would come out, you would get identity matrices. So it's essentially a very simple transformation, and it's kind of boring in a way. So when people design autoencoders, they always have to think, how do I avoid this identity matrix transformation? So does anybody have any ideas how to prevent this identity matrix from appearing?
Add noise.
To what?
Add noise to the incoming data.
Add noise to the incoming data. So let's see. 0 identity, which is bad. And the possible solutions is one, add noise to
How does it help?
Do you have a question?
My question is, how does it help? So you change your input data, but identity still works.
If you change your input data, identity will give you some result. However, it will not perfectly reproduce the result. So there's actually a very nice diagram in the book or the slides about what happens. Okay, so here's an example of learning an autoencoder where you add noise. So essentially you have a 2-dimensional input, and you add some noise to that input, and then you try to fit a neural network so that it reconstructs the input back. So what would happen is that it learns this particular function where when you give it a point on the manifold, it will return it unchanged. If you give it a point away from the manifold, it will push it towards the manifold. So this is a very interesting property of autoencoders. They tend to learn the underlying manifold or underlying space where the data is. Does it make sense? So basically the identity function would give a greater error in this case. That's the difference. And the reason is that the input data is not random. So some input data points are more likely than others, and your neural network can figure that out. And if it gets a point which has never been seen before, it can kind of figure out where to push it so that it's on the original input. So any other ideas? How can we avoid?
Constrain it, reduce the dimensionality in the intermediate states,
Mm-hmm.
like have a principal component analysis where you
Mm-hmm.
reduce the succinct number of meaningful components.
Right, so this is known as the bottleneck. So the idea is you would reduce the number of units in the hidden layer, so now you're no longer able to fit an identity matrix. So in particular, your W1 becomes 1 by 2. So your W1 is 1 by 2 in that case, and your W2 is 2 by 1. Well, your shape, you cannot put an identity matrix into the shape, so it will have to learn something else in that case. Any other ideas?
Eigendimensions? It would learn the eigenspace?
Would it learn the eigenspace? Yes. So in a very specific case of a linear autoencoder with a squared error, it will learn the eigen
Principal component, the first
yeah,
eigen.
principal component. Yeah, so to get some intuition, why? So suppose you have some data that's spread over an axis. Your H is a one-dimensional axis. So essentially, it will need to learn some vector where the W1 matrix, you're doing this. So you're doing W1 times X, and W1 is this shape, which means it's a projection on a one-dimensional vector. And then your W2 is the opposite. So if you walk through the math, going through the applause, you will figure out that it gives you an alternative characterization of finding the principal component. So this W1 in this formulation will actually learn the eigenvector of the covariance matrix of the data. So if you recall from earlier lectures, if you have the data, you can think of fitting a Gaussian to this data, and or an ellipsoid. So if you fit a Gaussian to the data, the level curves of the Gaussian are ellipsoids, and the principal axis of the ellipsoid is this main eigenvector. Back to avoiding learning the identity transformation, which is boring. Can anybody think of any other ways of avoiding this boring transformation?
You can add a nonlinear activation to the layer.
You can add. So in the example above, so here, you will replace f with f hat, which could look something like sigma w1 x. And if this activation is ReLU, you can say it's x for x greater than 0 and 0 upwards. Okay. I think you guys could just write this chapter. We're just going through all the ideas and introduced. Any other ideas?
You could add an additional criterion towards responsibility.
Right. You could penalty, so criterion on what? On the hidden layer? So you can say penalty on hidden layer. Penalty on okay, on the hidden units, right? On the hidden representation. Right. So one example, you could try to model this data, and you would require that for any data point, at most single unit here is non-zero. So that's a kind of a sparse autoencoder. It's not a very practical penalty because this is not a smooth kind of transformation. So there's various approximations, costs which approximately make it sparse. So again, I'll talk about it later. Any other ideas? So another idea, you can regularize the weights. So you can regularize. You can regularize them or constrain them. For instance, if your W1 and W2 were square matrices, but you constrained that the entries are greater than 1/2, then you cannot have an identity matrix because the identity matrix has ones. Similarly, you can, instead of constraining it, you can have a penalty. You can penalize it by the sum of squares of entries, and it works as a soft constraint, but it also will prevent it from learning the identity. Are we missing any?
Could you have more hidden layers than more hidden units than you need in your layers?
Would I have them?
Yeah, you could do that.
Yes, you could do that. So you could do that, but if you don't apply one of those strategies, you have the same problem as in this. You can just learn a matrix. It's not an identity, but it will have an identity as a submatrix. So for instance, if you have three units in the hidden layer, your learned autoencoder can end up like this: so 1, 0, 0, 1, and then these ones can be 0. So essentially, this is known as an overcomplete autoencoder, and it will have the same problem, and you need to use one of those techniques, except this one. Okay, another technique, you could also add noise to the hidden units. Okay, so let's go over the slides and see if we missed anything.
Can you enter a full screen on the slides so they're not cut off like that? Oh, you have them as PDF, right? You don't have, or no, it's a key.
Command Shift F if you want to show that. Once you're full screen. I'll press the green.
Oh, okay.
Can we go in like, yeah, to the beginning?
Where? 3, nonlinear activation.
So, no, you do you.
Okay. So let's see. How to avoid trivial identity. So you can do, this is the bottleneck layer that we went over. Right, so all this section is about just limiting the number of units. Have less units in the hidden layer than in the input layer. And this section is, you could have the same number of hidden units as input units or more, which is known as overcomplete autoencoder. However, you must follow some regularization strategies. So denoising autoencoder, that's the idea. You're adding some noise to your input data, and then you're trying to reconstruct the original uncorrupted data. You can add noise to the hidden layer. So for instance, you can randomly set some of the units to 0, which would be this dropout on the hidden layer. And then I'll talk about that later. A thing known as contractive autoencoders, which is another kind of regularization penalty.
Is your mic still on? Sorry.
Testing,
I think it's just too far from your mouth.
testing.
Or maybe it's off. Never mind. Maybe it died.
Yeah. No, it works. Why is somebody complaining?
I don't know. I just like looked at the spikes. Never mind. Don't worry. Be
Okay.
ahead.
Yeah, so in contractive autoencoders, it basically gives another way of regularizing the weights. And later I'll show that for the case of linear autoencoder, the contractive penalty is the same as just the regular L2 penalty on the weights.
What the intuition behind these techniques are? Is it because autoencoders might not learn the thing that you're trying to train it on?
Right. So autoencoders, it's kind of an artificial task. There aren't really any practical applications for them. So people try to add those techniques so it does something interesting. So what happens if you don't apply those techniques? It'll just very quickly converge, and the result is not very interesting. So it's kind of the subjective how to get it to do something interesting, and people have studied ways how to interpret the output. So earlier I showed a picture with manifold learning. So that's one way of interpreting the output, that it learns this manifold. So sparse autoencoder, you can penalize. The size of the activation in the hidden layer, or you can penalize the number of non-zero activations. Denoising autoencoder. So in this chapter, sometimes he talks about the probability formulation. So in practice, they're sort of equivalent, but if you are to make sense of this notation, the idea is that you're trying to model your data, and you're assuming that in the probabilistic standpoint, you're assuming you have some hidden, you have some probability distribution which generates your hidden data, and then from there you're generating your observed data. And people who like probability distributions, they, instead of fitting a neural network, they look at this problem as fitting the parameters of those distributions, which tend to produce very similar kind of algorithms. So, yeah.
I have a question on the previous slide. So actually, there is a corresponding page number 508. It talks about picking a point from the hidden parameter distribution. So instead of
508?
50.
Yeah, you just scroll past it.
509?
It's about it.
But 508 is before.
Maybe my page number was screwed up. The section 14.2.1.
14.2.1?
Yeah. To go down, the next slide. Further down. Yeah, this particular equation. So what is mentioned here that we can think of the autoencoder as approximating the sum with a point estimate.
Approximating the what? The sum?
There is a paragraph just below this
Okay, the sum with the point estimate.
So basically, we are approximating this equation with a point estimate of the hypothesis or the hidden layer.
Mm-hmm.
My question is, does it cause? Are there some implications of doing this?
Other applications?
Implications of doing this, basically, we are just using a point estimate. We are not using the Bayesian sense.
Right.
So is there will the model be able to generalize unseen data?
Well, my feeling is that the reason it's done, it's for practicality. It's just not practical to do the full integration. Maybe you would get better results if you did a full Bayesian approach.
Yeah.
So yeah.
The only justification is computation.
Yeah.
Sorry, can you repeat the question again? Sorry, I didn't hear.
The question was, so in this section it talks about, the chapter says we can think of the autoencoders approximating the log likelihood with a point estimate for just the most highly likely value of each. So the idea is that you have some input points, and then there is a range of possible values of each. So when you're trying to reconstruct the input point again, you would integrate over all possible values of your hidden code. And to make things tractable, instead of doing the full integration, you're just picking the most likely value of the code, and from there you reconstruct. And doing this makes this probabilistic approach essentially the same as running a regular neural net. So there's a lot of literature on variational autoencoders, where they go a step further and do something more advanced than just using a point estimate. So that's the illustrated picture. Does it make sense? I guess we went over that. Score matching, I'm going to skip this.
Why?
I don't quite get this part. And I've never seen it used. So this is the same diagram. This is the diagram. Oops. Okay, so that's the same diagram. What happens if your data lies on this manifold? Your input is two-dimensional, and you learn an autoencoder where you are adding spherical noise to each point. So the idea is, when you train it, you take a point, then you move it in a random direction uniformly by some random amount, basically a spherical Gaussian, and then you're learning transformation, which maps that point back to original point. So that's that's sort of a toy illustration that you're learning this manifold. For the case of digits, it's not going to be two-dimensional, but the idea is that there is some lower dimensional representation, and then each point on that manifold will actually represent something which looks like your training data. So if you have a bunch of digits, you can learn an autoencoder by translating those digits to different amounts, and then if you're adding noise before reconstructing, your autoencoder will learn this manifold. In a sense, if you give it some random noise, it'll modify this noise to look more like a digit. So this slide talks about what happens if you do the contractive autoencoder. So the idea of contractive autoencoder became popular a couple of years ago. It's an alternative way of regularization. So the regularization term you do is the penalty is you're penalizing the norm of the Jacobian Fourier transformation. So I'll explain what this means in a bit. So the penalty looks like this. So this term means the derivative, and this is the squared norm. So what does it mean in the case of 1D reconstruction? So in 1D reconstruction, you're learning a function, and a function is 1-to-1. So this derivative is simply a single number. So essentially, when you're doing a contractive autoencoder, you will learn a function which tries to reconstruct your points, but the slope is as small as possible. Does that make sense?
The gradient is with respect to the input pixels?
Yes.
Okay.
So essentially, you're adding a soft constraint that your function should be as flat as possible in a sense. And it's known as a contractive autoencoder because if you look at any point, if you, as you move your input around that point, you want, or what happens after you feed this contractive autoencoder, if you perturb your input point a little bit, the output doesn't change much. So you can see in this case, you can take x0, you can perturb it, the output will stay identical. So that's an extreme case, except for this point where it will jump. Yeah.
Is it the general purpose of regularization exactly this thing? So learning that manifold very confidently. So if the input is a little noisy a little bit, you still arrive at the same classification score.
There seem to be a lot of connections with that. There's various learning theorems which guarantee that if your classifier is stable, meaning small changes to your data doesn't change your learned classifier much, then you can have some guarantees how well it will read the future data. So yeah, so this is an idea that keeps coming up. You want your tuning procedure to be stable and not be affected much by the changes in your input data. Okay, so what would happen if we applied this penalty? So this is a simple example in 1D reconstruction. So what happens if you're doing our linear autoencoder example? So let me simplify some things. Let's say that we use h of z is equal to w1 of z. So then my function end-to-end f of h of x is equal to w transpose of x. So now to apply this contractive penalty, we're interested in the derivative with respect to x. So this is matrices, but it turns out that when you take derivative with respect to x, it works the same with the scalar case. So it is true that derivative of that thing is equal to just w1. So now we're interested in the squared norm of this derivative. So squared norm of Anybody see this? So the squared norm of that thing is equal to just, well, this is the Frobenius. It's the Frobenius norm of squared. So, yeah, so that's the term you get. So essentially, if you have a linear autoencoder, the regularization term is actually the fourth power of W. So you can rewrite this as okay, I'll just leave it at that. So the point was that if you're doing contractive penalty, that translates, in the case of linear autoencoder, that translates to this kind of regularization on your weight matrices.
You have Frobenius and you have a square.
Right, Frobenius.
Contractive penalty.
So the penalty here is the sum of squares of entries in the matrix.
Is that a matrix?
Yes, because it's Jacobian.
It's the gradient.
It's the gradient. So notice here you have a function from x to x. So for instance, x has n dimensions. The f of x like this. The gradient of f of x, let's say x belongs to r to the n. Then this thing, it's essentially a matrix of n by n. So you have a function which takes a multidimensional point to another multidimensional point. And you can think of this matrix of x ij. It's a single number, scalar, which tells you how much ith component of the output is changed when you change the jth component of the input a little bit. So you have a matrix because you have multiple input dimensions and multiple output dimensions. So you have n squared different interactions. Make sense?
Yeah, I think I understand for this particular case because this is just linear transformation.
Mm-hmm.
But how does it help in other cases when we have nonlinear transformations?
How does it help? Well, it helps. It seems to help in practice. So this gives a kind of alternative way of motivating how to come up with the regularization terms.
I'm actually just looking for some intuition, but if it is just empirical.
Well, the intuition. So one intuition, as I was mentioning earlier, is if you have a training procedure so that perturbations in your input data doesn't change the output much. There is some literature from computational learning theory which says that this will have a good generalization. So it's not clear to me if that's really much better than just a regular auto-regularization, but it's just a novel regularization that people seem to be excited about. Okay, so what else? He talks a little bit about nearest neighbor graphs, which seems to be kind of in a different direction than the rest of the chapter, but I can describe this idea. So I guess he talks about it because earlier he talked about autoencoders doing manifold learning. So before people were looking at autoencoders, people were doing manifold learning already. And how were people doing manifold learning? So simplest form of manifold learning, you can just fit a linear space to your data, PCA. But people were interested in doing more advanced things. So a more advanced thing, you can try to fit a different space to a different region, you can fit many different spaces to your data. So one approach people used is you build this nearest neighbor graph. So the idea is you take different points, for instance, images, and then you take some neighborhood. You can use Euclidean distance to see which ones are neighbors. And then for some set of neighborhoods, you can fit a linear space which models that data approximately. So that's illustration of this idea. You have sets of points which represent neighborhoods, and then for each neighborhood, you essentially do PCA. So instead of doing a single PCA, you have a bunch of different PCAs. Okay, that section was a little out of the topic of the chapter. Okay, so here's the contractive autoencoder. So that's the penalty I was describing here. Okay, that's the last slide. Any questions? Let me run through the chapter, make sure I don't miss anything interesting. Denoising autoencoder. Okay, so one note, all the examples here, I used a single hidden layer, but actually you don't have to. You can just have many layers, and then let's say instead of 3 layers, you can have 5 layers. It's kind of an arbitrary restriction.
The PCA analogy still applies if the neural network is deeper. If it has like maybe 3 hidden layers instead of 1, but if it continuously shrinks to a bottleneck, if all layers are linear without any non-linear.
It would apply because if all layers are linear, then 3 hidden layers are equivalent to 1 hidden layer.
1 layer,
Equivalent in the sense that they're no more powerful. They're not equivalent in the sense that the training is different. Actually, you can have a purely linear neural network, and when you try to learn it, the optimization problem is actually highly nonlinear. And actually, if you train it, you end up with plateaus, you can get stuck, and then you jump out. And there's some research which analyzes neural network training by just doing purely linear neural network, and they show that the training has the same problems as regular nonlinear neural network, meaning you get stuck in a plateau, or you get converge slowly, or you don't converge at all, and it analyzes. Noisy autoencoders, covered that. Yeah. He talks about score matching. He mentions it, but there's no explanation of what that is. Learning manifolds, covered that. Contractive autoencoders. Predictive sparse decomposition.
So, question on the contractive
Mm-hmm.
encoders. So, when you have enough capacity, you can represent, you can basically represent an arbitrary step ladder function, kind of like, as in an illustration, right? But what's interesting about it when you have limited capacity and you're forced to trade off between having zero gradient for data points and
Right. So in essence, that function that he was demonstrating that goes like this. If you're trying to model this as a polynomial, you would need a very high degree polynomial. In order to have something like this, it's maybe like x to the hundreds. So in order to have those sharp jumps, you would have already. So this picture that he showed, that already shows the model has huge capacity. more realistic picture would be something that is just smooth.
So the difference between this and like a regular penalty on the weights is, I guess it's a different kind of smoothness.
Right. Yeah. So here the regular L2 would be. So for the case of linear autoencoder, the L2 penalty would be this. However, here we have it's actually a higher order. So here you can think of squares of entries. These ones would be fourth power. So I mean they're still similar. I guess this penalty for linear autoencoder would penalize large entries more, so they would be more concentrated.
With this type of formulation, it seems like any solution that W1 is equal to inverse of W2, right? If you're talking about linear.
Mm-hmm.
Then if you apply this constraint, when you're basically asking that the Frobenius norm would be minimum,
Mm-hmm.
isn't it just basically well, it's hard to think of reversible and Frobenius form the minimum, but it seems like something could be solved from within different
And also normally people don't use linear autoencoders. You would use some nonlinearity, so that adds another constraint. So, okay, this predictive sparse decomposition, that's what people used to do before autoencoders. I haven't seen it used much. I guess 2011, that's not that late. But the idea is that you have a two-stage process. So you have some encoder and decoder function that represent, so they represent actual probabilities. So you have some kind of a probability of h given x and probability of y given h. And you're trying to learn a code. Given that these probabilities are fixed for each input, you're trying to find the code. And then you're fixing the codes, and then you're trying to fit the parameters of encoder and decoder. And then finally, 14.9, applications of autoencoders. There is only one application here, which is information retrieval. So the information retrieval application is when you train a bottleneck autoencoder. So for instance, you have images, maybe 1,000 by 1,000 pixels. You would, that's a million input features. So you may have a bottleneck layer of 100 features. So you would do this, and then you essentially, it gives a way of indexing the images. And that's what people used to do before ImageNet, because now we know that ImageNet features actually work pretty well for indexing and retrieving images.
What's ImageNet features?
So essentially you train ImageNet and then like AlexNet, so some kind of a well-performing classifier, and you take
the last submax layer?
Take the last layer. So that seems to work well. And actually one more application, it's not really an application, it's just something that produces pretty pictures, but there is this course by Andrew Ng called Unsupervised Learning, Deep Feature Learning, and one of the exercises is to train an autoencoder on the MDS digits, and you add the sparsity penalty, And what happens is that so what happens when you train an autoencoder with sparsity penalties on a missed digits, it essentially learns to see the strokes. So the sparsity penalty, in that example, you have a big hidden layer, but you're saying that for each example, only a few features should be active. So essentially, you're trying to represent each digit, like 7, as this stroke plus this stroke. And you're trying to limit those features so that they're being reused across other digits. And what happens when you train this sparse autoencoder, it essentially extracts the strokes. So you can see like the curvy stroke, the straight stroke. Right? Yeah.
Why would anyone use an autoencoder as opposed to just regular vanilla CNN?
Right, well that's, in practice, there aren't many practical applications. One potential application is, so people sometimes attach autoencoder to the original supervised training procedure. So the idea is if you don't have a lot of data, you can train your regular supervised loss, but also you're attaching autoencoders to each layer and then trying to train an autoencoder to reconstruct the layer. So people have used those hybrid architectures, so essentially it adds more constraints to the problem. But the reason, well, I guess there isn't really a good reason. It's more or less theoretical.
What other methods are popular in the unsupervised learning domain using deep nets other than this autoencoder?
Yeah, I can't really think of one.
If you look at the chapters that we have remaining in the part 3, like the chapters 13 for 20, like other things that you think like are the most useful ones that people use the most, like a more successful research in your humble opinion, stuff like that?
Let's see. Representation learning.
Oh.
Well, representation learning, so representation learning, the idea is if you have a good representation of your data, you can do any classification problem with a linear classifier. So actually, that was one of the motivations for autoencoders is if you learn this representation, then you can actually use this autoencoder to say, when you see a 7, instead of saying, I'm seeing this pixels are 0 and this pixels are 1, instead you're saying we have this feature and that feature. And actually, in that particular example, doing an autoencoder and then training a linear classifier on top of it gives much better results than training a linear classifier on the original pixels. So representation learning will probably matter. Structured probabilistic models. So this is one thing that was really popular 10 years ago, and people are still trying to make it useful. Partition function. I guess we may already have a presenter for the chapter. So the last two are for kind of a Bayesian approach to learning. Actually, the last 4.
Anything you've used out of those things in the
Yeah,
real
so
life?
so this is, if they were actually useful in practice, they would probably be in part 1 or part 2, the applied learning. So this is more of a research kind of, people are still trying to figure out how to use them.
Why did he skip reinforcement?
Why did he skip reinforcement learning?
he actually answered that sort of, like, he didn't skip it, but like they were writing the book, I think this was already online in 2015, and maybe it wasn't like as like hip as it is now.
Well,
Could it
there's
be?
already books dedicated to reinforcement learning.
Actually, I think the authors explain why they excluded reinforcement learning
Yeah.
in the introduction chapter.
Oh yeah. What is it?
What do they say?
Basically, it says reinforcement learning is like a whole topic on its own.
Oh.
Deserves its own book.
Oh, there
So
you
they didn't dare touch it.
Yeah.
The book, I think it's dense as it is already.
And reinforcement learning was really popular in the 80s, and there are some good textbooks that describe it. We don't really have any modern. So there's been some resurgence of reinforcement learning in the last 2 years. I don't think we have any book which covers that. Yeah. There's so I know Sergey Levin. He sometimes teaches. He taught a workshop on deep learning and reinforcement learning. So if somebody comes up with a book, it may be him. But you can find his slides on his homepage. Sergey Levin. Yeah, I think he's a Berkeley guy.
We have an open source deep learning course, deep reinforcement learning course.
Oh, really?
Yeah, so you can view all the videos and all the slides, assignments.
Oh.
Berkeley has it, right?
Yeah, deep reinforcement.
Where?
It's online.
If you Google it, you find it.
I'm sure you can. We just finished the actual class. And it was offered last spring and was being streamed online concurrently.
Do we have
Okay.
any more questions about this? Is everybody cool? Okay. Thank you, Yaroslav. We're gonna go to the town hall like we always do for anyone who wants to join us. It's a bar like a block and a half, 2 blocks away.
Oh, it's funny. The other deep learning club is discussing it right now. You can live stream. The other meeting group is meeting at the same time right now.
Yeah, that's unfortunate. Yeah, we should.
No,
Wait.
they're doing chapter 15.
Oh, cool.